We're going on to chapter 3 now of our book, and we come to the Fourier integral. We have dealt with the Fourier series in chapter 1. Then we went on a long excursion on complex variables. The long and the short of chapter 2 was that we went up to the Cauchy's integral theorem, and the whole purpose of the exercise there was to learn how to integrate stuff like something over something from minus infinity to plus infinity. You can have an e to the I kx on the top. You can have a sine kx, cos kx. We learned how to integrate that. And those integrals cannot be done by standard first-year methods that you learned. Even if you learned about improper integrals and so on, those integrals don't fall in that category. So we needed the residue theorem to find those integrals. Now that we know how to do that, the Fourier series is now going to grow up and become the Fourier integral. And the integral is going to require those kind of calculations using the residue theorem. So all these things are now fitting together. And then at the end of the game, we learn how to solve the heat equation. Heat equation and the Laplace equation. The Laplace equation is the wave equation. The heat equation, of course, as its name suggests, is the heat equation. Tells you how the heat is distributed in a rod or some object after some time t elapses. We considered short rods, 0 to L, or 2L if you like. But they were so-called finite rods. The question is, if you have an infinite rod, then you can't now use the Fourier series. Now we need some bigger tools, and this is the Fourier integral that will help us to handle that. So just recall, let me just recap. Recall the Fourier series. So we can write any function f of x in the shape sigma ak cos kx plus bk sin kx. K equals to 0 to infinity. As long as you can calculate these coefficients, you can write a function in that shape. And these coefficients were realizable in the form ak is equal to 1 over 2 pi integral minus pi to plus pi f of x cos kx dx, and bk likewise 1 over 2 pi integral minus pi to plus pi f of x sin kx. As long as you can do these integrals, you can then work out the coefficients, what goes in front of this. The Fourier coefficients were these things here. So that assumes that the period of the function was 2 pi. But if you want to make the period any number, like 2L, or 10 units, or 50 units, or whatever, then you have to modify that. Instead of minus pi to plus pi, you get minus L to plus L, and then you have k pi x over L in the place of kx, k pi x over L. I hope that rings a bell and it comes back to you. Or we can convert this to complex form. Where I can write the function f of x as some ck e to the I k pi x over L. Let me use a full-blown thing now. From k equals to negative infinity to positive infinity. That was a big thing there. Where the ck's are 1 over 2L integral e to the minus I k pi x over L f of x dx. So this will now have an analog in the Fourier integral. This sigma is now going to become a continuous variable, continuous entity, which will be the integral. The game is going to look very similar, but now sigma will be replaced by integral. This is for k equals to minus infinity to plus infinity, but still it's discrete numbers. Like minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. What about 1.5, you may ask? What if k is 1.5? Well, it's not a natural number, but it's part of the game. You can't just have a set of dots. A function like a heat, the way heat distributes itself in a rod, it's not like 1 degrees, 2 degrees, 3 degrees, 4 degrees. Somewhere it could be 1.5, 1.75, 2.3. It can take on any value between those two numbers. So then we can't make do with just this kind of formula. This is okay for small rods. But when things get infinite, then the game shifts dramatically. So these are okay for finite lengths. But for infinite lengths, we need the Fourier integral. So let me now define the Fourier integral. By the way, if you don't, or if you read the book carefully, it's quite lengthy, derivations and stuff. We don't need all of the stuff. I'm cutting to the chase here and telling you what we need exactly for the purpose of this course. The book is a bit more elaborate. So the Fourier integral theorem is like this. And you'll see it bears a strong resemblance to what we have above. So a function f of x can be written, I'm just changing it here, I'm reversing it, but it doesn't matter, as an integral of e to the I kx, f of k dk, from minus infinity to plus infinity, where this f of k is 1 over 2 pi integral minus infinity to plus infinity e to the minus I kx times f of x dx. This is known as the Fourier transform, called Fourier transform. So that transform, if you look above, look at this one here, the red one. Doesn't it look very similar? E to the I kx and something f of k is like the a ck. Where ck is 1 over 2l, you have 1 over 2 pi, if the interval was, if the period was 2 pi. 1 over 2 pi, e to the minus I kx, there you go, e to the minus I kx, the big difference is that the sigma is now this guy. And we've got this function f of k, which is obtained from this formula here. So if we give you some function, f of x equal to 10 or 10x, and we ask you to work out the Fourier transform, you plug in 10x e to the minus I kx, crank out the integration there using integration by parts, plug in these limits, or whatever limits are given in the problem, and then you get the f of k. Plug that into this, that will be representing this function as an integral. If you think back to the Fourier series, you may recall that where did that become relevant? When we were doing the heat equation, you might remember that you put ux naught, and that was equal to f of x, and you had to write the f of x as a sigma something. So even if you had 1 degree Celsius, you had to write 1 degree in terms of some kind of a sigma. That was making it more complicated, but you had to do it. Then you could match the two sides and say what the AK, big AK and BK was. Similar things going to happen here, except that now you're working out with continuous variables and not discrete variables. All right, so basically it's a formula which you can apply. So let's take an example, a very simple example. Expand f of x equals to 8 and 0 when between 0 and 1, let's say it's 8, and elsewhere it is 0, this function here. So to plot it, that's 8 between 0 and 1, but elsewhere it's 0. So we want an integral representation of that guy there. So we start off by firstly working out f of k, or capital F of k. Use capital for the Fourier transform. That's 1 over 2 pi integral minus infinity to plus infinity f of x e to the minus I k x dx. And in this problem here, it's 1 over 2 pi. The rod is only alive, the x is only defined between 0 and 1, so we can work with 0 to 1. We don't have to deal with the infinite integral yet. F of x is 8, so it's 8 e to the minus I kx dx. I just need to resolve this, calculate it. It becomes 4 over pi, 2 goes there 4 times. 4 over pi, and then I integrate this e to the minus I kx over minus ik from 0 to 1. Okay. Plug in the 0 and the 1 there, so it's 4 pi e to the minus ik minus, plug in a 0, e to the 0 is 1 over minus ik. You don't like the minus sign at the bottom, you can just sort it out. 4 over pi, switch it to 1 minus e to the minus ik over ik. Want to put the put the I on the top, then it becomes minus 4i. Minus 4i over pi 1 minus pi k, 1 minus e to the minus ik. So that is the Fourier transform. That's not the Fourier integral, Fourier transform. So now to conclude, I can say f of x is integral from minus infinity to plus infinity. F of k, which is minus 4. Let me just use that form there. Okay, minus 4i over pi k 1 minus e to the minus ik. F of k e to the ikx dx, dk. Watch on the top here. You see this dk here. Sorry. Here. Watch that. dk. Here it's dx. Why should it be dk or something else? Well, at the end of the game, so you can integrate this. Right? And at the end of the day, you replace the k by these limits. So what you will have left is a function of x with an x in it. You'll do the integration with respect to k, but then you replace k by some of these limits, and you will still have an x in the problem. So the answer is f of x. Likewise here, f of k, when you do this integration here with respect to x, you will replace x by some number 0 and 1. You will not be any x anymore, it will be a k in the problem. Like here. The Fourier transform has got a k in it. See here? There's no x. It's in terms of k. So then, this will boil down to 8 if 0 is less than x less than 1. It will boil down to 0 if, well, elsewhere. But what happens exactly at 0 and 1? Think back to your work on Fourier series. That's 8. Between 0 and 1, this thing is alive. Okay. What happens exactly at 0 and 1? Doesn't it converge to the midpoint of the interval? Remember, I even showed you a plot of this. I used Mathematica to plot those series, and I showed you it might jump, it might create some wave here, and then it jumps to the top. So in jumping, it goes to the midpoint. So you can say that it'll go to the midpoint 4 at the points of discontinuity. These are the jump discontinuities. It converges to the midpoint of the jump discontinuity. Any questions? Anything not clear there? Take another example now of a sawtooth function. Oh, sawtooth. Saw means like a saw that you use to cut wood, not like a saw tooth. Hey, I'm getting quite poetic now. It's a good play on words. Now, sawtooth is like a saw, the teeth of a saw. You do know what a saw is, like, have you seen one? Yeah, kids these days, they don't know these basic things. It's a pity. Kids these days, they haven't climbed trees or done stuff that we grew up doing all the time. Have you climbed a tree in your life? Those of you that were brought up in the city area, have you ever mowed a lawn? Nah, come on. I have children, I don't think they have never done it. We live in a world of some cyber thing. Let's take example 76. Well, there's no need for me to make new examples here because these are common examples. Sawtooth function. So why they call it sawtooth is because it's like this: f of x equals to 5, or x rather, if naught is less than or equal to 5, say, and 0 elsewhere. But you know, these are periodic functions. So from here to here it goes to 5, comes back down there, and then in the next interval it does it again. 10. It's periodic, so it looks like a sawtooth. Okay, anyway, it doesn't matter what it looks like. Let's now try to churn out the integral, the Fourier integral. So we want the Fourier transform first, f of k. That's 1 over 2 pi integral f of x, which is x, e to the minus I kx dx. And the only part that's alive is 0 to 5. You can put minus infinity to plus infinity, but according to the definition of the function, only the part from 0 to 5 is alive, it's x. All the other parts are going to be 0, by definition. This sawtooth thing I'm recapping from the first semester on the series, which converges to every 2 pi converges to the same thing. So now we'll have to hit this with integration by parts. Let u equals to x, then du is dx. Let dv equals to e to the minus I kx dx. Then v will be the integral of this, which is e to the minus I kx over minus ik. This will now be uv minus integral v du. uv will be x e to the minus I kx or minus ik, and then we will plug in 0 to 5 there. Minus integral v du, minus times minus will become a plus 1 over ik, integral of e to the minus I kx dx, because du is dx, from 0 to 5. X minus becomes a plus because I'm subtracting this minus ik. Now let me just crank out the integral there. Okay, well, for the first one, if I plug in a 5 here, it will be 5e to the minus ik5. Subtract, then plonk in the 0 here. You put a 0 here and kill everything. So there's nothing happens with the 0. So all that happens here is that you have 5e to the minus ik5, or 5k, over minus ik. On this side, you have 1 over ik. Integrate this now, you're still going to do this, e to the minus ikx over minus ik, 0 to 5. Same kind of story here. So you end up getting 5e to the minus ik5 over minus ik. Now what's this here? I squared is minus 1, so it's 1 over k squared, plus 1 over k squared, in 2. E to the minus ik5 minus e to the 0 is 1. That's it. You can leave it like that. So finally, you can say f of x is integral from minus infinity to plus infinity, f of k, which is 5e to the minus ik5 over minus ik, plus 1 over k squared into e to the minus ik5 minus 1, e to the ikx dk. So you have a dk, because you will be substituting for k, and you will be left with x. You'll be replacing k by these limits, if you're actually doing it, that is. Okay, so that's a Fourier transform. Any questions so far? I don't think it's hard to implement. No? 1 over 2 pi. Ah, yes. Yeah, so, yes, we should have 1 over 2 pi everywhere. So we have it there. I just went on to do the integration by parts. You're right. We should have that everywhere. This would be 1 over 2 pi. That's right. The nice thing about that 2 pi story is that when we use the residue theorem, it has a 2 pi I in it, so that guy will always die. Frequently die, not always. Any questions that's not so clear to you guys? So the Fourier theorem, Fourier integral theorem, is like the Fourier series, but now on steroids. It's now no more discrete, it's now continuous. Sigma is now integral. And so integral means you can actually integrate and find it. Well, we actually won't need to actually integrate this. If you integrate this, by the way, we know the answer. The answer is going to be x if x is between 0 and 5. It's going to be 0 everywhere else. Remember, it's like this. That's 5 there. Y equals x. So at the point 5 itself, when x is 5, what will be the value of the integral? Halfway. It will be 5 over 2. At the jump discontinuity, the function always, the integral here will converge to the midpoint of the jump discontinuity. That's the general theme here. See? You saw this very clearly in the case of series because I was able to demonstrate it. I can't demonstrate it now. I can't draw a picture of this continuous function. Okay, now let me tell you how the residue theorem fits in. So sometimes to calculate that integral from minus infinity to plus infinity, you will need the residue theorem. Things will not be as straightforward as these integration by parts and stuff. So let me tell you how the residue theorem fits in. So let's make some notes. We may need the residue theorem to evaluate something like, well, integral from minus infinity to plus infinity. You will recall that we had this line integral e to the minus I k z f of z dz, and we said that it's 2 pi I, the sum of all the residues of f of z e to the minus I k z. Oh, let me write this nicely. F of z e to the minus I k z at each of these singular points, Zn. There could be many. In other words, to integrate something of this type, e to the minus I k z f of z dz, we use the residue theorem. One snag in the proof of Jordan's lemma, which I referred to yesterday, I didn't prove it, but I said that we require to implement what is called Jordan's lemma. We make use of a result like this. The integral of along a semicircle for f of z e to the I omega z dz goes to 0 as L goes to infinity. What is L? Well, you may recall that if we got some singular points, we're surrounded by a semicircle contour from minus L to plus L, and then we make L go to infinity. So this thing can be as big as possible. But in that instance, the integral on the semicircle becomes 0. For those of you that didn't attend yesterday, we modified that previous result. In a previous result, we had n of x over d of x, and I said n has to be 2 more or 2 less than the denominator's index. Like if you got x to the 6 at the bottom, on the top you can only have x to the 4, x to the 3, anything that's 2 less. But yesterday we included things like e to the I kx and sine kx. In that cases, you can have the denominator or the numerator being just 1 less of degree 1 less. Okay, I know this is quite a lot of stuff, but we dealt with it yesterday. And you should see the examples that we've done if you were not present. So here, it is taken that omega is more than 0. In other words, k is less than 0. What is k? Well, k is the stuff we use here. See, minus ikz. That integral is going to minus ikz. So what if k is more than 0? That's an important question. So there are 2 fixes, 2 resolutions. What is this? All right. There are 2 ways to resolve this problem. One method, which we will not be using, but I'll tell you anyway. I hinted at this before. So if you have a semicircle contour like that, we know it's in the upper half plane, it covers all those points there. Question is, what if you go below the plane now when omega is less than 0, which means that k is more than 0. Just to make that 100% clear, guys, notice here we have in the yellow guy, we have minus I, minus k. Here is a plus. So omega being more than 0 means k being less than 0. When k is negative, this thing is a plus. It's a bit of a play on the words here. But in any case, it's quite easy to follow the calculations. So I'm dealing with the part below the thing now, below the x-axis, the lower half of the plane. So what you do is you have a contour like that, and then what you carry on the contour in the lower half plane. And come back there. So now you have a complete contour, like a figure 8. You can make a figure 8 without taking your hand off the paper. This thing here, you go around there, go there, down there. Changes direction now, and then go back. We're not going to do it that way. This is to continue the contour in lower half plane. That's one approach. You'll have to do negatives of the contours. Let's now focus on a different approach which we will be using. A clever observation by Jordan himself. Resolution 2. So f of k, you recall, is 1 over 2 pi integral minus infinity to plus infinity f of x e to the minus I kx dx. Now, put k to be minus k. Let's consider f of minus k. It's like taking the negative bit. See what happens here? You get 1 over 2 pi integral minus infinity to plus infinity f of x e to the I kx dx. Okay, k is now minus k. If k becomes minus k, then you have I kx. But that bit of gymnastics means that what we actually have there, so recall, what is the conjugate of e to the I theta? What's the conjugate of e to the I theta? Isn't it e to the minus I theta? Like the conjugate of cos theta plus I sin theta is cos theta minus I sin theta. Okay? So I just simply realized that, hey, hang on, this actually is the conjugate of f of k. The fact that this is now positive is like the conjugate of f of k, of this thing above it. Minus becoming a plus is a conjugate actually. That observation by Jordan now helps us. Or we can write f of k, if I conjugate both sides, is a conjugate of f of minus k. This is the crucial result here. So this will be for the part k more than 0. Jordan's lemma covers k less than 0, which is omega more than 0. We'll stop talking about omega now because it's confusing. It's like opposite signs. So let me show you an example. Okay, so this is called complex conjugation. You can write this word here. Complex conjugation. And it was discovered by Jordan. Take an example which will make it very simple. There's only one example I have now. Find f of k. In other words, find the Fourier transform if f of x is a function 1 over x into x squared plus 1. Suppose you have a function of that type. How do you find the Fourier transform? F of k. In other words, can you write this as an infinite integral with e to the ikx next to it? What is the requirement for that? Okay, look, let's just implement the theorem. So, what is it? The result? F of k is 1 over 2 pi integral minus infinity to plus infinity f of x e to the minus I kx. Dx. So it's 1 over 2 pi integral minus infinity to plus infinity e to the minus I kx over x into x squared plus 1 dx. Now you see where yesterday's work comes in. How do you compute this integral? That's what I did yesterday. As was done yesterday, you can only handle that. We have complex roots here, plus minus I. That's a residue theorem. What happens when it's a real constant here? X minus 0. Because the real part, will actually sit on the x-axis. Prior to that, all the roots were complex. I said they appear in complex pairs, conjugate pairs. But yesterday's work dealt with the real root. We had resolved what is called a principal value of an integral. But look, even if you missed it, it's easy to follow. So we have to find the poles first. Find the poles. We treat that as a z. So the poles are when the denominator is 0, z into z squared plus 1 is 0. That implies z equals to 0 or z equals to plus or minus I. So plot these poles on the axis. Z equals to 0 is at the origin. I is on the top. Minus I is at the bottom. Then you throw around that a contour, semicircular contour. And we find that there are 2 points that lie in the contour. In fact, this real pole belongs half in and half out. That was the story yesterday. We said that the way to solve that is to go around here and sneakily bypass this guy with a circle like that and carry on our merry way. You create a circle, a semicircle of radius epsilon, and you make the epsilon equal to 0. And then it turned out that in the residue theorem, you don't have a 2 pi I anymore. You have a 1 pi I, half the integral. Okay, so let me now return. Therefore, f of k. I apologize for keep on saying f of, but that's how you say it. F of k is 1 over 2 pi I. Yes, now the residue theorem. So for the pole I, you have, it's 2 pi I residue of e to the minus I kz over, look, it's z cubed plus z, isn't it? If I multiply it out, at the pole z equals I. The residue of this thing here, change the k and x into z. E to the minus I kz over z cubed plus z. X cubed plus x is z cubed plus z. Plus. Now this pole here is a double, it belongs to, it's half in and half out. So it's pi I. Residue of, same thing, e to the minus I kz over z cubed plus z. And that's at z equals to 0. And look at how easy this can be, guys. I promise you, to calculate this integral here, you won't be able to do it in first year calculus. Don't be wrong if you want. To calculate this integral, you'll simply not be able to handle it in the first year techniques that you learned. Integration by parts, splitting up the denominator, all kinds of tricks that you came across. It simply will not yield. But this elegant approach here tells us this is 1 over 2 pi I, right? 2 pi I Now, how do you calculate a residue? You simply differentiate the denominator, e to the minus ikz, over, differentiate the denominator as 3z squared plus 1. And you plug in z equals I. Plus pi I, repeat that, e to the minus ikz, differentiate the denominator, 3z squared plus 1. Of course, here you'll plug in z equals 0. And so now we are ready to finish it up. 1 over 2 pi I, this will be 2 pi I, plug in I here, so e to the minus I times I. Minus I times I will be minus I squared, which is 1, e to the k. Right? No mistake. And here, 3z squared, 3i squared is minus 3. Minus 3 plus 1 is minus 2. Plus pi I. Now here you plug in 0. E to the 0, of course, is 1. And the bottom 0 plus 1 is 1. There we go. So it's 1 over 2 pi I times. This is minus pi I e to the k plus pi I. Okay, I think you can see that pi I can cancel off. So it becomes 1/2 1 minus e to the k. And importantly, this is valid for k less than 0. Because I worked in the upper half plane where Jordan's theorem works, omega is more than 0, but k is less than 0. Because the formula has got e to the minus I k z. So now for k more than 0, we make use of the fact that f of k is the conjugate of f of minus k. That's Jordan's idea. So I replace k by minus k here, and then find its conjugate. So let me do one thing at a time. Let me replace k by minus k. So 1/2 into 1 minus e to the minus k. Now what's the conjugate of that? What's the conjugate of 1/2 to 1 minus e to the minus k? Anyone? Anybody? Are you thinking it's 1/2 into 1 plus e to the minus k? No. Yes. You see, you are trying to conceal a guilty smile. You are thinking that. No, it remains the same because there's no I in the problem. This part didn't have an I. Sometimes it will have an I. The I is cancelled off. So it remains, it's a real number. So it remains as 1/2 1 minus e to the minus k. And this is for k more than 0. In summary, I can say f of k, well, look at them. Both look the same, except for the sign change. Here's f of k, for k more than 0. And here's f of k for k, I'm sorry, the first one is k less than 0, k more than 0. The only difference is that the k and minus k. K became minus k. Is there a neat, compact way to write the answer down? The answer is yes. You can write it as 1/2 1 minus e to the minus absolute k. And this is valid for all k. When k is 0, it will be 0. It will be known as 1. 1 minus 1 is 0. Half of 0 is 1. Is 0, yes? Okay. with 2 pi I. Yes, it will change the whole game. Right? Okay, let me just patch it up. I can't finish it because it changes things now at the end of the game, right? So let me just patch it for now, and in the next lecture I'll just deal with that aspect. So I had an I in error there. So from here I'll have to re-deal with it, right? So let's stop here and I'll deal with it in the next lecture. Thanks for pointing that out.